Hello, in this video we are going to talk about the nuclei of atoms. Specifically, how many protons, neutrons, and electrons are in a specific kind of atom. Now, first, let's assume that the atom is overall electrically neutral. So we don't have any extra negatives or extra positives. Everything is going to balance out. So that would tell us that the number of protons is equal to the number of electrons. So we have an equal number of positives and negatives that are canceling each other out. Now, the atom that I was showing you in the previous video is actually an atom of carbon. And carbon is a very abundant element. It is present in pretty much every part of our body. It's present in carbohydrates. It's really just everywhere. Now, each carbon atom has 6 protons in its nucleus, and that must mean it has 6 electrons if it's electrically neutral. Now, one way that we can determine the number of protons that's in an atom is by looking at its atomic number. So the atomic number is given the symbol Z, and that's going to equal the number of protons in the nucleus. So if we look at our periodic table here, let's look at the atomic number, which is going to be right above the symbol for the element. So hydrogen has 1 proton, since its atomic number is 1. And let's jump all the way over to helium. Helium has an atomic number of 2, so helium has 2 protons. And then we could keep going. So lithium has 3 protons, beryllium has 4, boron has 5, and we can, keep going. Now, if we assume that the element is electrically neutral, that means that element also has the same number of electrons. So hydrogen also has 1 electron. And if we go over to helium, helium has 2 electrons. So super easy, right? So grab your periodic table and let's do this practice problem. How many protons does each type of atom have? So first, boron, second, nitrogen, third, iron, and fourth, chlorine. So pause the video, see if you can figure out the number of protons for each of these atoms. Okay, so let's look at our periodic table for boron. Boron is right here, and it is number 5 on the periodic table. So that means that boron has 5 protons. And then what about nitrogen? Let's look at our periodic table. Nitrogen is right here. It's right after carbon, and its atomic number is 7. So nitrogen has 7 protons. All right, next one is iron, which is Fe. So iron is right here. It's in the middle of the periodic table, and its atomic number is 26. So that means it has 26 protons. And the last example here is chlorine. So that has the symbol Cl, and it is towards the upper right of the periodic table. So chlorine has an atomic number of 17, so that means it has 17 protons. So not too bad, right? Once you can actually find the element on the periodic table, you can very easily determine how many protons it has. All right, so next question. How many electrons does each type of atom have? And you can assume that the atom is electrically neutral. So if you want to pause the video and try that on your own, you can. All right, so earlier we said that if an atom is electrically neutral, it will have the same number of protons and electrons. So on the last slide, we figured out how many protons each element has. So boron had 5, which means it has 5 electrons, if it's electrically neutral, right? So that must mean nitrogen has 7 electrons, iron has 26, and chlorine has 17. So far, hopefully everything's pretty easy. The most difficult particle to figure out is the neutron. How many neutrons do we have in an atom? Well, we need one more piece of information before we can figure that out, and that is the mass number. So the mass number is given the symbol A, and that is equal to the sum of the number of protons and the number of neutrons in the nucleus. So down below, we have an equation. We can rearrange our equation so that the number of neutrons in an atom is equal to the mass number minus the atomic number, which remember is the number of protons. All right, now there is a way to symbolize this to make it a little easier. Typically chemists will write the atomic symbol in a large letter there, and then on the upper left, they'll list the mass number, A, and on the lower left, they'll list the atomic number, Z, which again is the number of protons. So the carbon atom that I showed you earlier, we said it had 6 protons and 6 electrons. Now, it also has 6 neutrons. So, for example, carbon's mass number is 12, and since it has an atomic number of 6, we'll just subtract that from 12, and that gives us 6 neutrons. So you will always be told the mass number for an atom if you're asked to figure out the number of neutrons. Or you might be given the number of protons and the number of neutrons, and you'll be asked to figure out the mass number. So you'll always have 2 out of the 3 pieces of information. You'll never have to just guess, right? Okay, so one easy way to figure out the number of neutrons is to take the difference between A and Z in that symbol we were just talking about. So take the difference to get the number of neutrons. So let's do some practice problems just to see how this works. So down below I have some symbols for different elements, and I've listed the mass number up above and the atomic number down below. So again, that's A over Z, where A is the mass number and Z is the atomic number. So now we want to figure out how many protons, electrons, and neutrons each atom contains. So I'm just going to put some headers up here: protons, electrons, and neutrons. We'll just make a little table. So let's start with A, and we'll do this one together. So remember, the number of protons is equal to the atomic number, which is going to be on the lower left. So hydrogen has 1 proton. And remember, the number of electrons will be equal to the number of protons, and we'll assume that all of these atoms are electrically neutral. So that means hydrogen also has 1 electron. And then the number of neutrons, remember, is going to be the difference between the mass number and the atomic number. So A minus Z. So for this atom of hydrogen, we're going to subtract 1 from 2. So 2 minus 1, that gives us 1 neutron. All right, so try the other 3 on your own. So you can pause the video to do that. And when you unpause, we'll go over it together. All right, so let's try oxygen. So this atom of oxygen has an atomic number of 8. So that means it has 8 protons. And we already know then that it has 8 electrons. Now for the neutrons, we need to take the difference between the mass number and the atomic number. So 18 minus 8, and that will give us 10. So this atom of oxygen has 10 neutrons. Now the next one is fluorine. So fluorine has an atomic number of 9. So that means it has 9 protons and 9 electrons. And then for the number of neutrons, we're going to again take the difference between the mass number and the atomic number, and we get 10. And the last one is carbon. So previously we looked at an atom of carbon that had a mass number of 12. This atom of carbon has a mass number of 13. So the mass number can be different, which means the number of neutrons can be different for different atoms of carbon. And this is true for other atoms and elements on the periodic table. So we'll talk about that next. But this particular atom of carbon has 6 protons, 6 electrons, and if we take the difference between mass number and atomic number, we get 7 neutrons. All right, so hopefully not too bad just yet. So I just mentioned that different atoms of carbon can have different numbers of neutrons, which means they have different mass numbers, right? So these are called isotopes. So that atom of carbon that had a mass number of 12 and the atom of carbon that had a mass number of 13, they are isotopes of each other. Now, notice that the number of protons stayed the same. So protons never change. That's what identifies an atom. The number of protons will always stay the same for a particular element. But the number of neutrons can change. So let's talk about isotopes some more. So previously it was thought that the number of neutrons would be the same for an element. However, it was found that atoms can have different numbers of neutrons, even though they have the same identity. So one example is shown down below. We already talked about hydrogen and how it has 1 proton. and 1 electron. Now, that means it has 0 neutrons, right? So 0 neutrons. But there is an isotope of hydrogen that has 1 neutron, and that's given a special name, deuterium. Now, there's still only 1 proton and only 1 electron, but now we've added a neutron. And then there's another isotope of hydrogen called tritium, which has 2 neutrons. Still only 1 proton and 1 electron, but now we have 2 neutrons. So the mass number for hydrogen is just 1. The mass number for deuterium is 2 because we have 1 proton and 1 neutron, and they both have a relative mass of about 1. So it's just 1 plus 1. And then tritium has 1 proton and 2 neutrons, so that has a mass number of 3. So notice that the isotopes are getting heavier as we add more neutrons. So let's look at some other examples of isotopes. So most elements do exist as mixtures of isotopes. So for some elements, one particular isotope is going to be much more abundant than any of the other isotopes. So again, for hydrogen, if we look at its 3 isotopes, so we've got the isotope with a mass number of 1, the isotope with a mass number of 2, and the isotope with a mass number of 3. So you can see 1, 2, 3 there. The first isotope, the lightest isotope, is 99.985% abundant. So that is going to be the majority of hydrogen atoms. The second isotope, which we called deuterium, that is abundant at about 0.015%. So that's a really tiny amount of the atoms of hydrogen. And then the third isotope, which we called tritium, it's pretty negligible. They're very rare atoms. However, if we were to collect a sample of hydrogen atoms, again, we would find that about 0.015% of them are deuterium atoms, and the rest are likely going to be regular hydrogen atoms. Now, notice off to the side, I have 2 columns, atomic mass and average atomic mass. So each isotope has an atomic mass. So the first one is about 1.0078. The second isotope has a mass of about 2.0141. And the third isotope has a mass of about 3.016. So these are more exact masses than the ones we were referring to earlier, the mass numbers. So if we take the average of those 3 numbers and take into account how abundant they are, we get an average mass for hydrogen of 1.0079. And that is the value that's shown on the periodic table. So actually, if we go back, bear with me, I got to go back to a periodic table. There we go. If we look, oh, this one doesn't have the masses on it. Oh, that's not great. That's not a very useful periodic table. But if you use the one that's on your Canvas site, that one should have the masses listed underneath the element symbol. So for example, if we were to look at hydrogen, the atomic number would be above and the mass number would be below. So that's where this number's coming from. the average mass of all of the isotopes of hydrogen. Now, the next one that we can see is carbon. Carbon has 3 isotopes as well. So there's carbon 12, where its mass number is 12, carbon 13, and carbon 14. So notice that the carbon with a mass number of 12 is the most abundant at 98.89%. And then carbon 13 is abundant at 1.11%. And then carbon 14, there's only trace amounts of that atom in any sample of carbon. So we have very distinct masses for each of those, and if we average them, we get a mass of 12.011. And then last but not least, we've got oxygen, and that's just showing the same thing. We have different isotopes of oxygen. They each have different relative abundances, and they have different atomic masses. So if we average those, we get a mass of 15.999 for a sample of oxygen. Now, you'll notice I put a question mark up above here. That was referring to this unit, AMU. What is that unit? So this is an abbreviation for atomic mass unit. Now, earlier I mentioned that the mass of a proton is about 10 to the negative 27 kilograms. Same with a neutron. And then electrons are about 10 to the negative 31 kilograms. So those masses are so small. And that's a really hard number to work with, right? So chemists like to use a unit other than kilograms or grams to express the mass of an atom. So they came up with this atomic mass unit. Now, they decided to define the atomic mass unit as 1/12 the mass of a carbon-12 atom. And notice that sometimes instead of AMU, chemists will use just U for atomic mass units. Now, previously, some scientists wanted to use hydrogen as the definition for an atomic mass unit because its mass is 1. So that would be really easy, right? Other scientists wanted to use oxygen and say that the atomic mass unit was equal to 1/16 of an oxygen atom. But eventually everyone agreed that carbon would be the standard for this definition, so that's why it's 1/12 the mass of a carbon-12 atom. It was just kind of arbitrarily chosen in a way. But that is going to actually be equal to this value, 1.661 times 10 to the negative 24th grams. But don't worry about that. We're just going to use atomic mass units because they are much easier to interpret. Okay, so let's look at how to calculate that average mass for each element using its isotopes. So again, the atomic mass of an atom is equal to a weighted average mass of its isotopes. So remember, isotopes have different numbers of neutrons, and therefore they have different masses. So we're going to use the equation shown down below, where atomic mass is equal to the relative abundance of the first isotope times its mass plus the relative abundance of the second isotope times its mass, and then we could keep going if there were more isotopes. And then we divide that by 100. So, for example, let's use carbon and its 2 most abundant isotopes. So the atomic mass is going to be equal to the relative abundance of the first isotope times its mass, which is just 12. And then we're going to add the relative abundance of the second isotope times its mass, which is 13.003. Oh, that's a plus sign in between there. And then we're going to divide all of that by 100. So that is going to give us 12.011 atomic mass units. And again, if you look on the periodic table from our Canvas site, you'll probably notice that underneath the symbol for carbon is 12.011, and that is the atomic mass for carbon. All right, so let's do one more practice problem with isotopes. So let's say that boron consists of 19.78% boron 10 with a mass of 10.01 atomic mass units, and 80.22% boron 11 with a mass of 11.01 atomic mass units. And we want to calculate the atomic mass. Now, this is a slightly different way of representing an isotope. So boron 10 just means that we have an atom of boron with a mass number of 10. Now, what is the atomic number for boron? Well, remember, if we look at the periodic table and we find boron, the atomic number is right above the symbol for boron, and it should be 5. So again, we've got the mass number up above and the atomic number down below. But we really just care about the mass number right now, right? Okay, so let's make a little table. So we have boron 10, and its mass is, or its relative abundance, I should say, is 19.78, and its mass is 10.01. And then the other isotope here is boron 11. And remember, every atom of boron will have the same number of protons, which is 5. So its relative abundance is 80.22%, and the mass of that isotope is 11.01 atomic mass units. All right, so using the formula on the last slide, see if you can calculate the average mass of this element, boron. So you can pause the video, and when you're done, we'll go over it together. All right, so let's write the equation here. The atomic mass for boron is going to be equal to 19.78. I meant to write times the mass, 10.01, plus 80.22 times 11.01. And we're just going to divide that all by 100 just to get rid of the percentage. And that should give us 10.81 atomic mass units. So if you look on the periodic table under the symbol for boron, it should list the atomic mass as 10.81. Now remember, atomic mass units, you can either abbreviate as AMU or just U. Either one is fine. So that's why I use two different units here. They're the same though. All right, so I think we'll stop here, and in the next video we're actually going to talk about electrons more. We've talked about neutrons. Now it's time to talk about electrons. So I will see you then.